Welcome, everyone. My name's Abder Elandaloussi, manager in Southern California Edison. We're a utility in California. How many people have heard of Southern California Edison? All right, so about 5 of you. Good, great. So we're a utility that essentially operate almost all of Southern California. We have about 50,000 square miles of territory. We have millions of poles, so we have a very large territory. We operate our distribution system as well as our transmission system. So we're a DSO and a TSO in a way, I guess. But we don't do all the functions of a TSO. So we also have our CAISO, who also have some responsibilities in our transmission system. And so because of that, we get a chance to really have problems that go across our grid. And so we get some very unique challenges. Now, operating the grid separately like they do in Europe also presents challenges because now you have to ask permission and the data transfer. So we all have our own challenges, I guess. But today what I'm here to talk about is digital twins for electric utilities. And I really want to just try to define it, talk about some considerations for us that we're looking at to implement a digital twin, and then some applications. So the agenda is I'm going to talk about the background, drivers, the definition, some core components, the use cases, existing initiatives, and a specific SCE initiative that we're undertaking as we speak related to digital twins. And this, on the right side here, this is the report that we published through IEEE this year, which was a major effort. And this is going to be the foundation of part of my conversation today, and because it was a joint effort, and because of that we came to a certain understanding of what digital twins are. So the background, we were instructed by IEEE, which is the C-grade equivalent in the US, to write a white paper that covers the overarching definition and the vision for digital twins for the electric industry. And really, the idea is to drive innovation in new products, services, standards, processes, and even regulation. And the reason why all this is important is because there's too many definitions today of what a digital twin is. Too many, right? We often mistake, or not mistake, even confuse digital twins with ADMS, DMS, OMS, DERMS, and you can keep going, right? Anything that has data that comes in and spits out some insight, we call it a digital twin. And so maybe we're right, maybe we're not. And part of this collaboration, we had utilities, vendors, research labs, and even regulatory. All of them were involved in this initiative that I'm talking about here. So what are the drivers for digital twins, right? This is based on what we collected as a consortium as part of this paper. The grid DNA is changing as we speak, and is expected to drastically be different by 2045. And 2045 is a key number because a lot of the states in the US have mandates to decarbonize and to electrify and have a certain amount of EVs in our grid by then, right? So 2045 tends to be a magic number for some odd reason. But regardless of that, our approach to plan, design, engineer, and operate the electric grid has not changed at the same speed as our expectations, right? So it's becoming more unpredictable, the grid, for us at least, right? The load is unpredictable. We don't know when they're going to connect. We don't know where they're going to connect. Sometimes one load moves, like an EV, for example. Generation is also unpredictable. We know that, right, with renewables. But also, if you think about DERs like battery storage, if you have mobile battery storage, that's a problem, right? If you have battery storage that has a control that's not just arbitrage, for example, and it does frequency regulation or other things, it's going to behave differently. And we don't really know how it's going to behave at any time of the day. Customers behave differently, right? They can make big purchases, make big investments in their home or in their businesses, and we don't know right away, right? And finally, assets, right? Assets are becoming unpredictable because they could at any point fail, right? We have wildfires. We have so many things in our grid that makes our assets not predictable. We can't just follow that depreciation that the accountants do or the depreciation that the vendors tell us. Existing models used are often outdated due to large backlogs, right? So whether we make planned or unplanned changes to our grid, it does not reflect back into our actual models that we use to do our planning and everything, or operations. They don't get reflected in real time. I mean, it's impossible. The backlog, because we have such a big grid, is growing, and so that leads us to having incorrect models. It's difficult to integrate context into engineering functions. It could be the difference maker for more informed decisions. And what's context? Context is beyond just the grid. It's societal, socioeconomic, it's climate, it's maybe something to do with topology of the ground, whatever else can impact our grid. Because we're not in a vacuum, right? Our assets exist in a world where there's cars driving, there's birds, everything can impact our grid. There's woodpeckers, whatever it may be. And so because of that, how do we really integrate context? And to do that today, imagine how much you need to do via Excel, or even using Python and using traditional methods. It's really hard to bring in context in time and space, meaning, right? So how can you relate some sort of data set to your grid? Existing simulation tools that leverage physics-based simulation may not be adequate for the complexities the grid will face. And that means it's talking about single-dimensional simulation. When you do simulation today, right, you do SIME, right, or whatever else, Synergy or any open platform. But what that does is it provides you steady state, and then you have your dynamic stability, and then you have your protection, you have your communication. And so all those are single dimension, but really our grid is not a single dimension, meaning one change in one dimension will impact a lot of other dimensions, right? There's a complexity here. And finally, big data holds tremendous value, but it is underutilized in existing decision making. People are scared. They're either overloaded by the data, it's data overload, or they're too scared to even manage it, because when you have terabytes of data, where do you start? So the digital twin definition, and this is very simplified. The report has a more refined version, but it's a high fidelity, virtual, and visual representation of system of systems representing the electric grid, its surroundings, and any relevant context. And a system could be something like a capacitor bank, a feeder, a substation, or the entire grid. It's the fidelity of that system depends on what the use case is. But it could be even something within the capacitor bank. Maybe it's the actual capacitors. Maybe it's the switches within that cap bank. But the concept here is how far down do you drill down, right? And how much fidelity do you want? And that's really what a system can be. It's a multimodal representation of grid use case. Well, it's a multimodal representation of the grid, right? And what does that mean? That means, you can model your grid in different formats. You can have a LiDAR version of your electric grid. You can have your physics, your electric asset data. You can have your connectivity. So depending on your use case, you're going to have a different representation of a single point in space. So if you take like just a pole, right? Well, you can model that area where the pole is. You can model it in different realms, you could say. It just depends on what you want to do with it. It can be real-time or offline, and it can be used to analyze the complete state of the grid and predict the future state using a combination of AI and physics. And on the right side is a diagram just to kind of explain, potentially how you could think about different levels of technology readiness level of your digital twin, how sophisticated it can be. This is 2 dimensions where you have levels 0 through 5, and you can also represent it in terms of a model, the data, how they're connected, the uniqueness of that data, how granular it is, and the simulation capabilities you bring in. So the core components of the digital twin, we tried our best, right, to bring them into 5 separate areas. Model maintenance, you need to have a foundational model that can represent the grid in a high fidelity, and it should represent any system within this grid, right? And it will grow over time as your use case grow. It should be automated. There should be automation involved, and the humans should be in the loop right, towards the beginning to really validate that the model is being maintained properly. Simulation engine, multi-domain simulation engine. This is where you're talking about, you're looking at the grid from more than just one dimension at a time. And also integration of AI to augment traditional simulation capabilities. And that's really bringing the data and history. How has your grid performed? You bring that into your physics to really have a more realistic understanding of your grid and how it behaves. Interactive visualization, flexible, customizable interface to view your results and query the data and do whatever you need to do. Advanced multimodal data analysis, and then it should be responsive. This is big because when you talk about all this data, we can't forget there's computing behind all this. So how do you render this data? How do you move it between different areas within your digital twin? Model acceptance, managing the models for accuracy, usability, fitness for purpose, and limitations. This is about refining your models based on your use cases. You're not going to create a high fidelity model for every use case. That doesn't make any sense. Some use cases you can be very 10,000 foot level view of what kind of model you look at. But in other use cases, you're going to really need to dig deep and see, maybe you care about the windings in your transformer and how they depreciate due to a specific event, for example. That is a very specific use case, and it's just as important as a use case about a whole feeder or a substation or whatever. And finally, model validation, data quality, which is, we have separate models. We have protection models, we have planning models, we have operation models, and we have design models. So are those all the same, right? Are they all making the same assumptions? Do they have the same parameters? This is where you're talking about model validation, where you need to make sure every function within your organization is using the same assumptions. And today, they're not. Actually, I don't know if other utilities agree. Anybody else agree, by the way, on this one? All right, I got one. The rest of you, I'm not sure I trust you. Okay, so use cases. We have design, right? So designing the electric grid, there's a big, historically speaking, digital twins have been used in other industries to design, right? You conceptualize your design, you can use a digital twin to do that. Planning. That's a big case, which is what I'm going to talk about, the use case that we're looking at. Grid operations, being able to simulate how your grid would behave, and again, using physics and AI, and how do you have that fidelity to do so. Asset management, big use case. I think that's also a big use case in the aviation industry, aerospace industry. Generation, electrification, that's another big one. Can you create a model of your EVs? That way you're able to understand how these EVs moving around, how would they impact, well, it's actually modeling the chargers, but then the EV itself, each EV might have a different behavior at the end of the day. So how do you account for EVs by representing them as a digital twin? Protection, control, and automation, that's a big one I think that's not being looked at today, which is how to use a digital twin to understand the cascading effects of a protection action. Well, we do that in RTDS, but can we do that on a higher level even? Risk and compliance and cybersecurity, right? How does cybersecurity impact the actual physical world, right? Because right now, yeah, it'll cause an outage, for example. But really, if you actually go into the details of really what are you imposing onto your communication infrastructure, and then seeing how that propagates, it's more than just an outage, right? There's an IT aspect of this. There's also having to reset a bunch of different devices in your field. You should be able to simulate and understand the true effect of a cyber attack. So wildfires are a big thing here in California. And so digital twin could be used, and some use cases here include live holistic view and situational awareness of the grid, resiliency calculation and prediction and simulation of that resiliency. Resiliency is something that we really don't understand, and we're trying our best to quantify resiliency. But why quantify when you can just really look at the effect? Don't need to quantify. You actually see physically what will happen. Visually, you can see what would happen if you have the proper models. PSPS, public safety, public shutoff, impact simulation. So today, when there's a fire, we intentionally shut off and we isolate specific areas of our grid. And so what is the impact, socioeconomic impact? We understand the electric impact, but when you bring in context, now you can look at more than just that, right? You can look at how is society impacted, and that's actually a big thing right now is society and how our public is impacted. Planning, the PSPS as well, microgrid siting optimization, dynamic risk assessment, and then post-event analysis playback, which is after the fact, trying to understand really what went wrong and telling the story. It's a storytelling method. This is really what this is, in this case, is being able to tell the story better. Because our regulators always come back to us and ask us what happened, and it's called a data request, and we spend 2 weeks of our lives, 3 weeks of our lives scrambling around, collect the data, align it in time and space, understand to tell the story. And we always tell it wrong. And after the fact, we find out, this is what happened. If we want to do it right, it takes us a month, and we have to ask for more time usually. So architecture, this is a very simple slide, but just it touches on some things maybe that LF can support, and we can talk about more. It should be an open platform. It should be interoperable. And when I say vendor agnostic here, I mean it shouldn't be just dominated by one vendor, right? And that's the one thing that I always tell in every single conference. If you're one vendor that claims you can do it all, or even 50% of this, I will challenge it, right? And I don't want that to happen, because vendor lock-in is going to be the biggest challenge to innovate in this platform, right? To really get to where we want to go, we're talking hundreds of companies that need to come together that each provide specific part of this story. It needs to be uniform components across all the use cases. So all the use cases should have some commonality, right, to be able to interact and be interoperable. It should be scalable. The architecture should be scalable. Seamless application integration. Multi-domain simulation, we talked about that, right? How do we integrate multiple domains, not just the electric domain or protection or whatever? There's more to it than just that. Ontology-based data, so what are the rules and regulations around data and the standards around data? Cybersecurity, it needs to be cyber secure. When you bring all this data in, right? Now you're almost, and you have, vendor, you have interoperability and everything. How do you ensure that data never leaves when it shouldn't? And then a diverse data set integration. I should be able to take societal data, economic data, just as much as I should be able to take LiDAR and images or electric data, right? So it should not be it should not discriminate on what data you have. And on the right side, this is very, very simple, but you have a single digital twin data ingestion management layer, and then you have your different vendors. They each have a proprietary algorithm. So the idea here is, instead of a vendor going out and building a whole software to do a specific application, just build the intelligence and plug that intelligence in, understanding the rules of engagement with the data layer and the visualization layer. And so now you're able to maybe innovate a lot faster as a startup or a company, because you don't have to go and build everything around your IP. The IP is not your visualization, most likely, and it's not the data portion. Everybody can do the data portion. It's about the intelligence. So let's focus on that. That's really where we want to go with the digital twin. Opportunities for innovation. So I took a step back and I said, okay, well, what should people really work on? Network model management, a common digital twin framework, and that's really part of this discussion here. Existing solutions integration. So a lot of softwares have already been developed, right? All these people are making some really interesting things, but can we integrate some of those into this platform that we want to build? Computation, right? Quantum computing, whatever it may take, it's going to take a lot, because we're trying to do, when you bring in data of various nature and bring it all together and ingest it in different ways, we're going to be pushing the boundaries of where we are today. Model interoperability. And that's, different types of models. Again, not just electric, think about other models, right? So how do you create this interoperability? Use case development, and use case could be wildfires. I mean, the use cases could be hundreds. It's really up to everybody here to figure out what that use case is. And then finally, application development. And that's a little bit different than use case. Application is the enabler of the use case. So you could build even more use cases if you think of another way to model that data. So this is the SCE kind of project in one slide, right? We called it MADS, Machine Learning Augmented Digital Simulation. The problem that we're trying to solve is existing PowerFlow engines generally assume static grid configuration, capacity, asset ratings, and performance. And this can result in a suboptimal load flow analysis that leads to suboptimal decision making. For planning purposes, this is. So what I mean here is, when we go and run our simulation, we have some parameters we start with, some of them we guess, right? And we just run it, and we just pray that it's going to converge, right? And the problem is, half of those parameters might not be valid anymore, right? Meaning that cap bank might not operate at the rating at which you thought it would. It's not going to give you the voltage difference that you thought it would give you. That transformer might not do the same, might not have the same ratios as you thought it did. So how do you bring in reality into our PowerFlow? How do we make these assumptions? Maybe either make them less important, right, or make them more accurate. So depends. This is the conundrum we're in. The objectives of the project is to improve the PowerFlow engine results by augmenting those results with the digital twin platform to analyze the grid data and integrate predictive analytics into the engine, right? And we want to demonstrate a situational, context-based PowerFlow engine. And the three main components: we're going to build a data and model ingestion, cleanup, and integration layer. We're going to build this algorithm that has machine learning plus PowerFlow, and then we're going to have visualization of these results. And the outcome is we want to integrate operational and non-operational data to reflect real-world conditions. And this is where context comes in. So we want to bring in context, whether it's satellite data, whether it's LiDAR. What will help us improve the PowerFlow? That's what we're about right now. So we haven't ironed out exactly what data we want to bring in, but this is the hypothesis. And on the top right there is a paint drawing of mine that I did to talk to our executives and convince them of this. Yes. It's all. Yeah. So take a whole presentation and make it into a picture. Yeah. Actually, so here's a funny story. So somebody who was like 4 levels above me, which was a VP or director or whatever, I was going through this presentation, I had all these words, all these cool things, and then I showed her this image. She literally stopped me. She said, "Why did you just show me this from the beginning?" That's literally what she said. So yeah, so I learned my lesson. It really does it goes far. In conclusion, big data will become a liability if we don't collect, store, and leverage it efficiently, effectively, and in a timely manner. If we sit on data and we're sitting on valuable insights, or we sit on things that we didn't realize, it's going to become a liability for sure. Combining insights from data with traditional simulation could optimize decision-making processes. Are the existing assumptions for simulation accurately reflecting reality? That's the question. Are they, We need innovation in standards, technology, and processes to make the digital twin framework a success. The grid is rapidly increasing in complexity, but the tools are not changing at the same speed. And finally, the digital twin is a scalable, open modular system of systems platform that maintains a high-fidelity replica of the physical grid and the context in which its assets exist. It brings together the necessary processes, technologies, and applications that maintain and leverage that digital replica to efficiently operate, maintain, plan, design, engineer, and monitor the grid. So there's a lot of words there, but really, I mean, you had to, it was a challenge iterating the definitions, but we had to iterate to a point that satisfied a utility who was very early stages, right? No IT stack, versus one like us who were fortunate enough to have a lot of investments in the IT OT space. And so for me, I just jumped straight to AI. For some of them, they're like, whoa, like we don't even have sensors, right? So we had to kind of bring it all together here. So with that, there's a final thing here. There's an article that was recently published called the Digital Twins 2.0, and I took a very radical approach to describing digital twins and really why they're important. So anyway, it's on the Transformer magazine. But anyway, if you want to get some good sleep, you should read it for sure. Any questions? Yeah. Yes. Sorry. That first portion was? What about them?
Well, if you have real-time use cases within our company, we have operational technology and information technology with different stacks and different solution spaces. Did you think of a solution for that as well in the framework?
So are you talking about addressing the online versus offline, right? And you're saying that the online is more of OT and the offline is more of IT, right? Yeah. So we do, this is the layer that bridges those two gaps is what we're trying to go, right? Is we're saying, first of all, the real time, right? That's the most risk and it will have the most pushback, right? Because operators are the last person I want to talk to about this, to be honest with you. Why? Because they have the whole grid in their hands, and the last thing they want to do is have any mishap. So the idea here is start with the offline, get the credibility, and we have to get credibility with our own organization, and then you move into the online, right? But yes, it will be an it will be a cloud solution, right? It should be a cloud solution, but yes, it should have the ability to stream data, because at the end of the day, it's still a data ingestion layer, right? So you can stream it whether it's real time or you can do it in batches. I don't know if that answers your question though, so. Well, partially, yeah, we can talk more. Any question? Yep. Can you give him the?
So from a architectural perspective, you went through the components of a digital twin, and one of those components was the simulation layer. From an architectural perspective, do you include the simulation layer with the wider digital twin of just basically saying this is what's happening or this is what the logs indicate, et cetera, which is more of like a telling you what the data is saying rather than here's what we think it will do in the future? Is that integrated together or are those two separate components?
So that within itself is an application that must be built, right? Because it depends on your use case, right? If your use case is just trying to understand what happened in history, you don't need simulation, you just need data, right? But if you're trying to say, okay, I want a more realistic understanding of what could happen in a year, and I have my scenario, which is what I'm basing all this on. So all forecasts are wrong, by the way. They're forecasts, right? The question is, you have as many scenarios as you need to feel comfortable with your decision. So in your question, if you combine the two, what you're doing is you're trying to say, can I understand the grid's history and learn from it, but then combine that with physics, right? And so the architecture, because there's an applications box, those vendor boxes that I had, it could be a use case which is just pure data, or it could be data plus physics, or it could be just physics, right? Or simulation, not just, it could be more than just physics. Yeah.
Hey, Abder, thanks. This is great. You and I have been talking about this for a few days already, and it's really nice to see the details, finally. So I wanted to bring up something. You may know we've been doing this project with DOE called Regrow, which is essentially to replay the heat wave of August 2020 in California, because all sorts of things happened that no one anticipated. No simulations have reproduced those results yet. So it's a really challenging problem. What we discovered when we sat down to do this is that a lot of the data that you need to reproduce the event was never recorded. So for example, if you go back and you ask, what were the forecasts that NOAA was telling people, those weren't saved. So we don't actually have the forecast from 2, 3, 4 days before of what NOAA was telling utilities. So it might have been saved by some, but there's no systematic saving of all of the information that was used during the course of that event. So, and we've learned this for a long time, that nobody saves ambient data, right? You only save interesting data. But it turns out the ambient data dominates what these learning systems are doing, not the weird events that are on the outliers. And so I'm wondering, in your discussions and preparation of this, how much of that question came up, and what were people saying about what are we going to do? How are we going to save all of this, supposedly non-interesting data that ends up being the basis of all the training and all this stuff that no one thinks matters but actually does?
Yeah, that's a great question. And that conversation came up in a different manner, but what we did understand is to have proper AI or proper machine learning to, understand history and make some predictions or find anomalies. To find anomalies, you need to know what clear blue sky is, right? Blue sky conditions. And so because of that, storage, which as I understand, storage is the cheapest thing you could do, right? And so for us, storing historical data to train future models is going to be necessary. So we are thinking about that step. But we, as a utility, are a little bit advanced than other utilities who, like I said, barely even got to this point where they even have data to store. And so, yes, so for us, since we are at the stage where we want to deploy AI models, we fully understand that we need to go back at least 2-3 years. I mean, we store 5 years worth of AMI data, but data like what you said is not regarded important until something happens, right? And so prioritizing the data, what data to store, I think that's an action item for me to bring up, because the more data we bring in, well, LiDAR, for example, are you going to really store that much LiDAR, right? Maybe you have to. So maybe we will go through some iterations where the first time around we store 3 years worth of everything, but then over time we start, prioritizing what's important and what's not. But that's a very good point. Didn't really talk too much about that. Right here.
In a use case for trusted energy, where the Alliance members are looking at the security and the authenticity of data, one of the key challenges in brownfield deployments is being able to trust the data that comes from RTUs and from whatever sources they come from. And we've been using the term digital twin for something at an edge gateway, which is the frontier of the security model, to the data sources from the RTUs coming in. There's certain normal expected ranges of data flow and all the metadata associated with it, and stuff that's abnormal. And we implement what we're calling digital twins within that gateway to detect whether or not we make a heuristic assessment as the trustability of that externally sourced data. Does that still fit within your understanding or definition of what a digital twin is, or are there other ways to describe that process? In effect, it's using digital twins to make heuristic or mechanized AI-driven assessments as to the trustability of data that comes from outside a secure environment.
Yeah, for me, that's a use case on top of this platform, because and this platform is just for the sake of example, but at the end of the day, what you're doing is you're doing like a digital footprint, like a signature that you're expecting, you're almost doing like an anomaly detection in a way. Is that right?
Yeah, it's anomaly detection, or one of the risks that we see in the future, particularly with the distributed energy ecosystem, is that you have large data sets from which emergent properties arise that previously were not seen or known, because it's such a complicated system. And we want to have adaptive twins monitoring the data sources from very diverse ranges of RTU inputs and so on, to make an adaptive decision about how much do we trust the information coming in, or are we under some sort of attack, or has there been some sort of failure which is systemic? It might be a solar wind farm where certain units have been told or have been misinformed that the wind has changed direction when it hasn't. That's a form of attack. So we want to be able to detect those things even though the underlying data is perfectly fine.
Yeah. No, I think the digital twin portion is not the actual anomaly detection, but it's all the data that you're bringing in together to characterize, what this device is, right? So you are building the digital twin of this device, but then on top of it, you're doing anomaly detection, right? And frankly, like, you can go and call whatever you want a digital twin at the end of the day, right? But right, you know what I'm saying? Like, a lot of people would say, again, SCADA is a digital twin.
Yeah, but then people won't understand what you're talking about.
Yes, exactly. And so in this case, I would call it anomaly detection, right, on top of my devices. Because we have something like this, we're doing it at the grid level, but we're doing anomaly detection, bringing various data sets together. And I didn't call that a digital twin. I'll be honest, I called that an anomaly detection model, right? But now, if you build it on top and you have some ability to predict things, and that's really where you have potential. Yeah. But that's just how we've taken approach. Any other questions? No? All right. Well, thank you all for your time.